Right, hello, welcome to defn episode 6. No guests, nothing else, just myself and VJ. How you doing, VJ?
Hello, Ray, I'm doing good. I think this is just, as you said, two village idiots talking about closure.
Yeah, I'm sorry,
no
people.
Experts to correct us.
Yeah, it's just going to be total BS this week, I'm afraid. Yeah. Right, okay, so should we do a quick follow-up from last time?
Of course. So last week we had super fun with Misha talking about Hoplon and of course some nuclear issues as well. Yeah. But it was very super fun to make, and I hope you guys enjoyed that one. So that's and we have been getting some pretty good feedback and from the Slack channel and also online as well on Reddit. We have been raising to the top every now and then onto the Closure subreddit page with spectacular 2-digit votes. So please keep clicking.
I haven't seen it actually. So we're up to 2 digits now.
Yes.
So this is very good.
It's fantastic, yeah. And it's amazing.
Oh, we've actually we've went into double figures on the defn podcast channel as well.
On Slack, yeah, that's true.
Yeah,
that's
so
true.
I mean, we're really building a huge community out there.
Yeah, now I'm actually sporting a fake mustache whenever I'm getting out of the house, because now I'm a minor internet celebrity. I'm looking out for paparazzi and everything. But it's been anyway. So it's been amazing, and thanks for your feedback. And so we've been before just recording, we were talking about JDK 8 support in Closure.
So I mean, actually, the reason why I was interested in it, VJ, was because I'm doing a little project to do with event streaming, actually, to do with Kafka Streams Library, which is a new library, you know. Yeah. But a lot of these big data libraries, I've noticed, we talked about this ourselves before. In fact, when we first met in the Amsterdam closure days,
Dutch closure days,
closure days, about the fact that Spark and new systems like this Kafka Stream Library, Flink, a lot of them have Scala APIs or JDK 8 APIs, but they don't have closure APIs. Even though closure and big data play very well together, the APIs don't seem to be coming out there. Now I know we've got some things that are dedicated closure-wise, like Onyx and stuff like that, for big data. But obviously the whole point about closure is to do interoperability and to leverage the work that's out there in the JVM community. So it's a bit of a shame that we're not getting this Java 8 interop, because we can't take advantage of these lambdas and streams and stuff like that. Actually, I'm saying that. There's a guy has written a library called ike.cljj that allows you to have some of these things. And he seems to be actively developing it, which is good. But I'm thinking that it would be very nice, even if we don't require JDK 1.8, to have some of the core team at least having a look at this interop, to make it a bit more core to the language. Because the thing I was saying before was that that we're going to talk about reducers today, and that requires essentially JDK 1.7. I know you can patch JDK 1.6 with some contrib library, but really, I think for all intents and purposes, it's a dependency on JDK 1.7, and there was no problem with that. Obviously, let's just do that.
Yeah, and also I didn't see anything in the on the dev.closure.org wiki as the next release planning. There isn't any discussion or something happening to support the lambdas or streams or having a proper interop, though. I'm not sure if there are any plans, but I guess we need to wait, I suppose, because 1.9, the major feature is specs, right? I don't see any other major things bundled into 1.9.
No, that's right. That's the big one. I mean, obviously, the thing about 1.9 is that and Alex Miller has said this, is that it will still only require 1.6, JDK 1.6. So there's no chance of them, mandating 1.8 for JDK for Closure 1.9. But they are doing it for some of their other libraries. So Datomic, for instance, now requires JDK 1.8. The latest versions of Datomic require JDK 1.8, which is of course sensible. I keep on saying 1.8, by the way. It's kind of crazy.
JDK 8.
You know, it's like because I'm such an old JDK guy
user.
It's not 1.7 and 1.6, is it? It's like
it's JDK 8 and Java 8 and Java 9 and I think it was the Java 5.
Java Software Development Kit 1.8 or something.
Probably, yeah.
There probably is some hidden 1.8 in there somewhere.
Yeah.
Anyway, so it would be interesting to find out if anyone else is kind of having similar experiences there with this lack of interop with JDK 8. I wonder if anyone is feeling that. And obviously, if anyone's listening from the core team, then it would be nice to share what was happening in that respect. Maybe if we get Alex on.
Then we can ask him.
We can ask him about that, actually. That's what we should do.
True.
Okay. Yeah. I think we've got our answer ourselves for that one.
Okay. So this episode is going to be about concurrency and parallelism. But before we get on to that, we have this news and events. And there are lots of things happening in Europe, especially. I think, of course, there is Euroclosure, the probably the biggest European closure conference. I don't know if I'm offending the Closure Exchange guys in London by saying that. But we have Euroclosure in October, I think, October 25th and 26th. And there is CFP still open until August 5th. And there is another event in Finland, Closure Tray, or Closure. I don't know how to pronounce this, but this is a pretty awkward name. But anyway, that is happening in Tampere in Finland. And that's on September 10th. And I saw that David Nolan is going to attend that event. I think it's a one-day event in Tampere, Finland. And of course, there is also Closure Exchange in the UK, in London. That is happening in December 1st and 2nd. And there is a CFP open for that as well. So any of these listeners, if you're interested in talking about closure, I think this is a good opportunity to apply for the call for presentations, both at Euroclosure and Skills Matter Closure Exchange. And apart from that, defn will be there at Euroclosure, as we've been explaining to our fans, which is plural, by the way, that will be there. And we'll have a powwow or something, a quick meetup during the Euroclosure. We'd love to talk to you guys and ask for new ideas. And I think there are a couple of ideas being suggested on Slack already, like what we should do, like speaker interviews and other stuff. So maybe we'll plan something.
We'll definitely try and, I think, get some interviews for the podcast while we're at Euroclosure. I think that would make a lot of sense, wouldn't it? But it would just be nice to, like you said, just go out and have a coffee or a beer or a water or a Coke or whatever, and just have say hello to people in person. It's always nice, isn't it?
Yeah, of course. We'd love to meet some of the people who are listening to this. It would be amazing to get your feedback in person, so you can punch us.
As long as they don't punch us in the face, it's okay.
Exactly. Yeah. So, or you never know. But of course, we've been very open about the way we offend other people. I hope there are not going to be any Scala people there. So we'll see.
Ooh.
Yeah, that's going to be a big problem. But anyway, let's get on to the main discussion for the topic for today. So, concurrency and parallelism. So, there have been a lot of discussions about or confusion about what is concurrency and what is parallelism. So, we're going to throw in our opinions into the whole confusion part, and then hopefully try to untangle it a bit.
Yeah,
so,
I think we're a bit confused ourselves, aren't we? So we'll just try.
That's true.
We'll just try and talk it through. I think this is like a therapy session, isn't it? Really, it's kind of like, what do you think? How do you feel? Do you have any problems as a child? I think did you have concurrent parenting?
I think we should start with, hello, my name is Vijay. I just Googled concurrency versus parallelism.
Yeah.
That's like a concurrency parallelism anonymous meeting.
Yeah.
But anyway,
well, the thing I always think about is concurrency is the thing that's confusing about concurrency and parallelism is, of course, it's all about things happening at the same time.
Yes.
So to some extent, if you say, oh, it's parallel, not concurrent, or concurrent, not parallel, you're kind of splitting hairs at some point. In the end, things happen at the same time. All that really matters, I think, in the end, is what programming constructs do we use for one thing versus the other thing, and what programming constructs. How does it benefit us to use the programming constructs for concurrency versus the programming constructs for parallelism? And I think that in the end, that's what's really going to matter, because you can get yourself tied into knots around what is because you start at the hardware. I mean, at the very basic level, if you've got one single core, then in theory it can only do one thing. But we know for a fact that operating systems hide that. In fact, hardware. If you have one CPU, it can only do one thing at a time. Yeah. So the whole point about operating systems is to fake the fact that you've only got one CPU. So if you remember, Linux and Unix, and I think that in the early days of Windows and DOS, of course, in DOS, when you were at the command prompt, you ran your command and you waited until the command came back.
So it's basically running one thing at a time.
And it's only when you get things like, modern operating systems with Windows and, or where you can make a background job. I mean, remember the Unix days? Oh yeah, we can do there's an ampersand. You can run a shell that puts this task
things
in the background. Yeah. A daemon process. Yeah. What's that all about? I mean, we have this devilish, literally. It's a devil. It's in the background. It's a devil, little devil in your machine, demonizing things.
So it's fundamentally evil.
It's fundamentally evil. Yeah. So you have these little background processes running there, and clearly, if something is in the background, is it running concurrently or is it running in parallel? Well, actually, you don't really know.
Yeah, that's true. But I think
if there's one CPU, then it must be concurrent in the sense that it's faked.
That's true.
But if it's got two CPUs or you've got a GPU with multiple resources, then of course it can be running in parallel, and you don't know that.
Yeah, but I think that the whole concurrency problem, or not even a problem, the concurrency came because of the whole time slicing, right? So you have multiple tasks to do, but you have only one thing that can do the things. So then you have this time slicing. So I'm going to allocate, 3 milliseconds of my time to do task A, and then next 3 milliseconds I'm going to do task B. But in the compressed view of human time, it looks like they are running parallelly because the task switching is so fast. So the concurrency...
Yeah, the computer kind of masks it by just being so quick.
Exactly. Yeah, so in my understanding, at least, as far as I understand, concurrency is essentially when you have just one thing that is going to do the tasks, but parallelism comes into the picture then when you have multiple things that can do the multiple tasks at the same time. So I think because nowadays we have this quad-core machine, so there is always some parallelism going on. I mean, we're now speaking on Skype that is running, and there is another program that is running in the background. I'm pretty sure the whole network monitoring shit and everything. So my operating system is already taking advantage of having multiple cores and running things parallelly. But if you switch to concurrency, then there are, as you were pointing out, both concurrency and parallelism mean that there are multiple things happening at the same time, but the way they're executed.
Well, I think the other thing to say is that like we've been talking about with the hardware, is that the operating systems take care of concurrency for you by either time slicing, like you say, or being aware that something is going to talk to the network or talk to a disk, so they can essentially swap that process out and give something else a chance to run. So they either do this scheduling via resources. If you're listening on an I/O or a network I/O or a disk I/O, then they can essentially put your process to sleep and give someone else the CPU because they know you're not going to do anything. Yeah. But and that's fine. But as you got through the 90s and the 2000s towards middle of 2000, like 2005, 2006, suddenly Moore's law runs out on a single CPU. So whilst up until that point, your computer program has just got faster and faster and faster.
Yeah.
Your computer could do more things because, like you say, it was just masking the fact that it was really swapping things out. So once you get to the point where actually you need to exploit parallelism in software, then it's a different ballgame, because suddenly the CPU, the operating system itself and the CPU itself need to cooperate.
Yeah. But
so if you think about it, like Windows, I was doing some research on this at work actually for like big data problems, and if I looked at the kind of the stuff that you need to do, and basically you up until like Windows, I think it was Windows. No, I'm getting me wrong. I might get wrong here, but I think it was Windows 2000 was the first operating system from Microsoft that actually used multi-core machines. Was capable of you. I think it could be faked in earlier versions, but in Windows 98. But I think Windows 2000 was the first one. Forget NT, but on the desktop, Windows 2000 was the first one.
Okay.
And in fact, Windows NT was written from the ground up, wasn't it? To support multiple cores. So that's my point, is that it kind of, the operating system had to be rewritten to take care of multiple cores. And what was interesting at that point was that if you were running, let's say you had some a spreadsheet, then if you had some if you were running like Excel 2000, then Excel itself was not capable of running multiple cores.
Yeah.
Because it didn't have the .NET framework.
Yeah, exactly.
Multiple core aware. So then they made the .NET framework like multi-core aware, just like Mac did with the GCD stuff. And then Excel was rewritten to take care of the multi-core parallelism. So my point is that multi-core has brought parallelism into the programming world, and that's the big discussion, isn't it now? With all these, functional programming and all this kind of stuff, and this whole notion of immutability, data,
exactly.
All these persistent data structures and the tree-based structures, which we'll come to in a bit more detail. But that's that notion of the hardware essentially requiring us to take advantage of its parallel nature is the thing which is changing in the last 5 years, last 10 years, let's say, but certainly the last 5 years. And you can no longer rely upon faster hardware bringing you any perceived benefits.
But I think in closure, I think the concurrency story is much more mature than parallelism story, right? I mean, because concurrency is one of the unique selling points of closure that people, or at least Richie even announced closure. So okay, this is the whole STM based concurrency, and then having immutability everywhere that helps you with shared state concurrency. So you have all these fundamental constructs, like you have the vars, refs, agents, and atoms, and then they are operating on immutable data structures. So if I remember correctly, you can achieve concurrency based on either shared state, I think. So you can share the memory, and there are multiple threads accessing the shared memory. So that's how you create one kind of concurrent programs. And the other way is basically something like an actor model, where you have this messages passing through different threads, and the data is passing from one thread to the other or one actor to the other. So that is actor-based concurrency or message passing-based concurrency, I think. So there are two different ways of looking at it. But in closure, the shared state thing was like the bottom or one of the foundational constructs with atoms and agents. I think that is one of the things that people, or at least we say STM is going to help you with writing concurrent programs without worrying about locks or writing synchronization by hand. So I think concurrency is much more mature in closure.
But I think that's like you say, that's like old school Java concurrency, isn't it? Where you have multiple threads all running, but trying to access a common state,
resource,
common resource. And that's definitely very old school, and you could do that in Java, but obviously it was much more complicated. The locking strategies were much more complicated in the Java world than they are in closure world. And that's the source of many bugs, isn't it? In kind of imperative and OO programming, is this whole notion of things not being initialized properly, off by one errors, the usual kind of crap that you get with these mutable data structures.
Yeah, but I think there is, if you see the different constructs, I think there is plenty of documentation available, like which particular STM-based thingy that you need to use in what case, because most of the things are, for example, if we if you use STM, then you need to use software transactions, so using DoSync or I think alter or DoSync. Yeah, DoSync is basically to cover the transactional operations on a given data set or given data structure. And also we have asynchronous stuff using agents. So atoms are essentially, if you want to share data between multiple threads without worrying about, okay, this is going to modify the you don't want to get the concurrent modification exception. So that's where atoms are going to help you with. So I'm going to put some data into an atom, and then there are other threads synchronously accessing the state, and at the same time you can also modify the atom itself without worrying about getting exceptions. So without using any locks. So I think that is the simplicity of using an atom instead of using lock-based concurrency or writing synchronized methods in Java. But then I think the other one is most popular one is atoms and agents. I haven't seen too much refs in the wild though. I'm not sure. Maybe the use cases are not really that interesting for the real world cases. I need to check. Maybe because there is also a difference between the coordinated versus uncoordinated change of the data. So if you want to change any data in a ref, for example, then it has to be part of a transaction. So you need to do that in DoSync or a ref set, I think. There are a couple of functions available.
Yeah, it's complicated, isn't it? Because of this, the ordering of things and the optimistic things, and
and also the
deadlocks as well.
And also retrying, because if it fails, it's going to retry.
Basically, isn't it? So
yeah,
I think the use cases for that kind of stuff is a bit like two-phase commit. You know, it's theoretical, all very nice, but no one ever does it. You know, because it's just horrible for performance.
Yeah, I haven't seen any DoSync stuff much, but maybe, well, my Clojure code reading is not that much as somebody else would do.
Well, maybe we need to get someone to call us in
next
time around and tell us a bit about it. You know.
People who are using DoSync, please call us up, then let us know your experience. That'll be cool. But
it would be nice to understand the real world use cases, like you say.
Yeah. Because I didn't get any mileage from DoSync stuff yet, but STM stuff. But primarily, I think I wrote atoms. I mean, I use atoms everywhere, especially in Clojure script world. They're really useful.
Well, the agents are not available on Clojure script.
Of course, yeah. So anyway, so that's the basic.
I think the thing about atoms and stuff like that, though, is because it's all basically, assuming that you've got multiple threads accessing some common state.
Yes. Yeah.
So you get concurrency that way, but that's I think very different to the kind of the concurrency models of things like JavaScript, which I think is really the basis of concurrency we really want to talk about today, isn't it? Which is things like core. Well, also based upon this notion of Node.js and stuff like that. So there was a lot of these concepts that actually, to write an efficient HTTP server, it's not a good idea to and Java people knew this, of course, before JavaScript guys did. Jetty and Comet and all these kind of things knew about continuations. But that's what you need to do. You need to basically, rather than using a thread per request, which is very hungry on the memory, you need to use one thread or a very small number of threads, and basically park the sessions or the states for the inactive threads until you get some I/O coming back.
Yeah.
And that's the basis of Node.js. But obviously the problem with Node.js is this callback crap that you get, this Christmas tree code where you end up saying, all right, I'm going to do something in my callback, and then I'm going to do something in that callback, and I'm going to do something in that callback, and the other callback. Oh my God. Once you get beyond about 2 or 3 levels deep, it just becomes totally horrible to reason about. And that's why they call it callback hell, isn't it? Because
because you have no idea of the execution of the program, and you can't
compose it. That's the problem.
Exactly. Yeah. And also you cannot make a mental model of the program, because you keep thinking, okay, this happens, and then it's like a huge mess.
Well, it becomes a Christmas tree in the code, because you start off in the middle with like 20 characters, then it becomes 25 characters, and as you indent out, it becomes like this huge. I'm 400 characters to the right all of a sudden. Oh Jesus! Yeah, so that's a nightmare. And of course, what these guys do now in the JavaScript world is they use these promises, still a bit Christmas tree-ish, but eventually they're going to move, I think, to this async await stuff in ES7. But this is what the Go language has for a while, and that's what this core async does now, isn't it? Is this concept of a block of code, which looks like it's just sequential code, but will happen when some data comes into a channel. So it's essentially a callback model, but that callback happens
in the code transformation, or at the lower level, because the code, when you read it, it still looks like imperative or
it just
step
looks
by
like
step.
Sequential code. Absolutely, it's very easy to reason about. But underneath it all, I think they're basically these things like Go loops and Go blocks. They're just basically macros, aren't they?
They are. I think that is one of the things that surprised, or maybe thing that people use as the nicety of Clojure or the Lisp world, is that you can just write a macro that can convert the code from that is looking like imperative code, and then that is converted into some sort of a state machine because during the compilation phase. And compared to Go, because in Go they have this language level support for these channels and Go routines, but in Clojure it's just a library. So
I don't know though, actually. I mean, it's a funny thing, isn't it? In some ways, I mean, I think it's a kind of like engineering wonder that you can make this macro. But it's got a problem as well, though. I mean, one of the reasons why we, people often say, don't they, about Clojure? It's like data first, then functions, and then macros. And yet, this is kind of like quite an important thing, the macro of the core async. But actually, you can't compose it.
That's true.
And I find that, I don't know. I mean, I'm not sure what. To be honest, I don't know what difference it would make if it was in the language, in terms of composability. I don't know.
Yeah, but in the language would mean the Clojure core need to change. So I think that is the.
I mean, you say that, but actually, it was Timothy Baldridge and Rich Hickey, and they are the Clojure core team. So if anyone wanted to change it, they had the power to change it.
Of course, but then it would be a special form or something. It will still be implemented as a macro, I would guess, but it won't be a library, but it's part of the Clojure core, and it will get the special treatment like the if and whatever the special forms that we have. But maybe that's, I don't know, maybe we should get Rich Hickey on the podcast, and then maybe we can ask him, what do you think? And
it would be interesting. I've never actually seen a thorough. I mean, I know that people talk about the macros thing, but I've never actually seen a proper, or never heard. Maybe there is such a thing, and I've just missed it. And follow up, welcome, But I've never seen a thing saying, it was a macro because this, that, and the other. Apart from the convenience factor of not changing the language, what are the real actual benefits? I don't know.
Not for the Go macro, but I remember reading somewhere that one of the libraries for probably Redis, I think, there is a macro that generates the code at the compile time for all the functions that are in Redis API that is specified in the JSON spec. So I think there are some use cases for macros. Probably Go macro is one of them. But of course, I either we're going to get Rich Hickey here and Timothy Baldridge onto the podcast, or we're going to, spend more time understanding this. And then we can come up with, okay, this is why this is a Go macro. or Go is a macro.
I mean, I think it's fabulous. It's been done. Don't get me wrong. I'm just saying that it is awesome that such a feat can be achieved. I just don't know enough about what the benefits would be the other way around. If it was composable, for example, because it's a macro, it's not easily composable. Maybe it's, that's a downside. That's all I'm saying.
That's true.
Whereas if you have them as functions and some kind of support in a language, then maybe it would be more more powerful even.
That's true, but when you think about as a designer of a programming language, it's all about trade-offs, right? I mean, you need to pick one way or the other. So every approach has its own advantage, and every approach has its own disadvantage. So you need to see what is the trade-off here. So making it a library and then not imposing it into the core, and also one of the things that in this case particularly is that channel-based concurrency is not going to be the holy grail for everything. So it doesn't need to get language level support. Maybe could be another speculation from my side, that because there are still other types of concurrencies models like actors and channels, and then of course you don't want to go to the thread level because that's too low level. So maybe there is still scope for other types. That's what I remember when core async was announced, and people were asking questions about why not actor based thing, because Rich Hickey said, I think channels are much more interesting way of implementing concurrency, not the actors.
Well, his argument about the acting thing is that the caller has to know the callee, and that's the big difference between the core async model, where you put some data on a channel, and you don't know what happens to it, and it can be picked up by many people listening on that channel, or many processes listening on that channel. And I'm a fan of that, definitely. And
there is a decoupling between
the caller and the callee makes the whole system more composable, I think, and more loosely coupled, which is something that we like, isn't it? So, and I think actually on the I can't remember the details, but on one of the closure things, there's I wouldn't say a denunciation of the active framework, but definitely a kind of like, we don't like that framework because of A, B, and C, and certainly the linkage between the typed messaging of the caller and the callee is definitely a big negative, I think.
Yeah, that's true. I think if you see Akka, for example, well, they're working on typed actors, so that might be there in the future. But so far, it's I worked on Akka without any typed actor stuff a bit. So actors can consume anything. So there is no typing involved. So that is where one of the nice stuff that you have in Scala world is that, or Scala, that you have these types, but then once you switch to actors, then the types are gone, and you send a message to any actor, and then it might choose to not to respond or not to consume it, or it will consume it, but it won't act on it because the method itself accepts any. So you don't know, and there is no compile time check to tell you that, hey, this I can only accept these kind of messages. But there is a typed actor thing happening there as well. But anyway, let's not talk about actors much, because I think channels are the way to go, obviously.
Well, actually, the interesting thing is that, like you're just saying there, you can now start to do things like put, specs around the data, for example.
Yes.
And you can do some interesting things there. But yeah, I mean, I've done a little bit of programming with the core async stuff, and it seemed very nice to me. I wrote a few blog posts about it, and I think there's some very powerful primitives and some nice ways that you can combine data. I did some time series stuff on it again, which was good. But the thing which I thought was, I was talking to a friend of mine from the Belgium meetup actually, and he was saying that in the Go blocks there was some problems with exception handling, and he found that in the end it was getting quite annoying to have an exception handler for every single statement almost in the Go block, and he ended up abandoning it and going to manifold from
Okay.
Zach
Yeah,
Talman,
Zach Talman. Yeah.
which was less or more consistent in that respect, less onerous. But anyway, I mean, I certainly found core racing very nice, and I think actually, to be honest, because I think core racing, like it or not, is the 800-pound gorilla in the concurrency world in Clojure. So, like it or loathe it, it's here to stay. And I actually like it a lot. So I'm not upset about that. But what I was going to say was that the nice thing about it is that you can have all kinds of filtering on stuff as well. So you can run these kind of transducers on the channel as well to transform the messages and to filter the messages and all these kind of things. And they're really incredibly easy to write. I was super impressed by that. At first I thought, whoa, a transducer, that's going to be hard. It's going to be a complicated thing. But it was so trivially easy. Sometimes you can get put off by the names of these things. But actually, it's just a simple map or filter function, and it does. Yeah, it's so easy to make the input of a channel converted to another. To either strip stuff out or to convert stuff to put on another channel. It's so easy.
Yeah, I think I had some understanding of transducers, so I was thinking that there is this seek abstraction. So any function that can work on a seek is going to work on this one. But then transducers are next level of abstraction that says, as long as I can ask for the next thing in it, that is fine. So obviously, because of the seek abstraction, you could use all these functions on vectors and lists and anything that is implementing a seek. But obviously, you cannot use that on a channel. But channel is also something like a collection. So you can ask for the next thing. Is there a next thing available? I'm going to work on it.
Yeah, it's a stream of events, actually.
Exactly. So you can treat the list as a stream of events or stream of things, and you can treat channel as a stream of things. Only the difference is that there is some sort of a time component in the second situation, probably. So the transducers are, in my understanding, it's the next level of abstraction that says, okay, I'm going to work on anything that is mappable, and that means anything that has a next thing available. So it could be a channel, it could be a collection, it doesn't matter. So you can just create a function that is going to work on anything that can ask for the next one, and anything that I can combine. So that's what my vague village idiot understanding of transducers.
Well, yeah, I mean, you're right. It's unifying. It's quite the whole stream thing is quite unifying though. Because you don't. Although you're right, you can inject time into these things. You don't have to. So you can. I mean, it's very easy, for instance, with core racing to have a timeout channel. So you can just say, okay, put a timeout channel in the mix, and your listeners can listen to either one channel or they can listen to multiple channels. And if you're listening to multiple channels, one of those channels can be a timeout channel. And when that timeout channel closes, you will get an event to say that channel is closed, and you can then react on that, which is a classic way to rather than using like a thread sleep, for instance. If you did a thread sleep inside of a channel, that would be bad. Yeah. Because one of the things you shouldn't do when you're in the channel world is do blocking operations, and of course sleep blocks on the thread. So you have to do. That's why these timeout channels are nice, because in the background it's doing some system sleeping thing. I don't exactly know how it works, but I'm guessing that's what it's doing. It's got a thread pool in the background, and it's using
of course there is one thread attached to it. I remember this. Sorry, go ahead.
And so anyway, my point is that while you're in the Go block, you should just be doing non-blocking operations. You should just be doing straightforward things that are all on the CPU, just transforming data or manipulating data. You shouldn't be doing sleeping or IO, or
IO, yeah.
those kind of things. Those should be
Yeah.
at the edge of your system. But it's really nice to be able to combine these operations informally. You just basically put some events on some channels, and then someone else can compose the way that these events are handled later on. So I think overall, actually, despite my notion of saying that macros and functions are not composable, etc., I think the core async model is actually very, very composable and very decoupled. So
Yeah.
I like that, because in the end it's the data on the buffer that you're modeling, actually. I was going to say the other thing that's worth discussing about with core async is this buffering concept, actually.
Yeah.
Because one of the problems with asynchronous operations is very, very aggressive writers or very, very lazy readers. This whole notion of back pressure is essentially a problem, because what do you do? There's always an interesting question. Is I'm writing a log file into a channel, and if someone doesn't read from that channel, well, eventually memory is going to get full, isn't it?
Yeah.
And something's going to go wrong. So what happens in core async is by default, things are unbuffered. So if you write something, then you can't write again until someone reads.
Yeah.
Okay.
So it's blocking.
Kind of, yeah.
Yeah.
But normally, of course, what happens is that you will use a buffer. So when you create a channel, you can say, okay, well, I'll have 100 or 1,000 or 10,000 messages as a buffer, so then what's interesting is then you have some different types of buffers, because you can choose to
dropping
what
buffer
to do.
or
So you can have there's like I think 4 different buffers. There's ones where basically if they're not being read out, it will drop your writes.
Yeah.
So in other words, it will be first in. So the consumer will see the first messages that you put in there.
Yeah.
Then you have these other ones called sliding buffers, where it will drop the messages that are already in the buffer and take your new ones. So this is
I think we should call them like first in, first die or something. If it is a dropping buffer, so it's going to drop from the first thing that gets in. If it is not processed, it's going to be dropped.
Right.
And the next one is going to. So it's probably first in, first die.
Yeah.
So then messages will be really careful getting into the channel.
Yeah. That's true. Yeah. But but I think what's interesting about it is that you have sort of control in your environment as to what policies you're going to apply to different messaging, different channels. So depending on the nature of the data
program,
you can choose to either drop it at the beginning or drop it at the end or whatever. And of course, the funny thing is that I think overall people don't like this dropping thing.
Yeah, that's what I initially, when I heard that, hey, there is going to be a dropping buffer, that means it's going to have some sort of a buffer capacity and it is going to drop the stuff. And if you think about it, in some cases it really makes sense. For example, if I'm tracking mouse movements, obviously I'm not interested in every movement of the mouse, and I'm only interested in the latest stuff.
Yeah.
So that is a reasonable assumption that I'm interested in 20 mouse movement path events.
And I only want the latest ones. Drop the earlier ones. Yeah.
Exactly. So if I'm not fast enough to process them, and it is fair enough that you drop them. And when you think about other cases as well, in the real world, people think it's actually losing data, but in some cases you're not really that attached to historical data. You're interested in what is the current one. So in that case, is that the dropping buffer would make sense. But that trade-off is going to give you more control on the program's behavior, as in I can be sure that this program is not going to die because of eating up a lot of memory. So I also
think that if you're really invested in this data, like this logging data or whatever, if you want to make sure you keep every message, then you have to use something which has got greater robustness than one single process. So that's why, to me, things like Kafka are so useful, because they're very large scale, distributed, fault tolerant, all these kind of things. So you get that kind of system. So it would be quite interesting if the Clojure guys are working on an equivalent of Datomic for core async. If you could imagine like scaling up the collections, which is what they've done. Essentially, they've scaled up the collections for Datomic, haven't they?
I think so. I'm not familiar with the Datomic code base.
Well, what I mean is that
at one point they're going to open source it.
You have a bunch of persistent collections,
which
are now durable in the database. So you know what's changed. They're all immutable, persistent collections, but now you can scale them up by persisting them on a disk somewhere and having multiple readers and all this kind of good stuff. If you can imagine that doing the same thing for core async, then that's kind of what you're doing with Kafka essentially.
Yeah, of course. I mean, at that scale, you wouldn't write just Clojure collections to deal with it, right? I mean, obviously, if you need that size of data, you need an external system to handle it. But this is good for most of the use cases where you don't have that so-called quote-unquote big data, which the stuff that doesn't fit into your memory. So it makes sense that for those any smaller use cases, it's just going to be okay. So obviously,
I think it's also, even for the cases of the Kafka, whatever, if you can read from a Kafka stream into a core async channel. Because it's really, to me, what core async is about the way you organize your code. But I only use Kafka as an example of basically making sure that if you're really caring about the durability of your messages, then that's what you would do about it, because there's everything in core async is ephemeral, basically. So if you want this whole thing to be durable, then you have to
you need Kafka
some message broker, basically. Yeah,
that's true. Anyway, so before moving to parallelism, I just remembered my train of thought has parked or arrived at the station. So now I recollect what I was talking about. I was about to talk about the futures, because that is also one of the things that you can use to achieve concurrency in Clojure, because that would tie in nicely, because for the case of parallelism, we have some way around, initially there was this parallel map, and that is essentially implemented as the P map, which was implemented as a future. Essentially, so for every function, so you have a collection of things and you do pmap instead of a map that uses future by allocating a thread pool of, I think, number of cores plus 2, and then you have a thread pool, and then that is what we use to actually execute the parallel mapping stuff. But other than that, there is a
that was a kind of poor man's fork join, wasn't it?
Exactly. Yeah. But I think reducers are the example of fork join parallelism, right?
Right. Because yes. So let's move on to reducers, like you said, because that's where we start moving away from this concurrency model.
To parallelism.
This core async. Yeah. Okay. Yeah.
Exactly. So basically, reducers, when they were announced, they are going to work on anything as long as they are foldable, I think. Like the transducers are on mappable, these are on foldable, anything that can be folded, and you have this list of or a collection of items, and then it will use the fork join framework to divide the given collection into smaller pieces, and then apply reduce function or the reducing function onto each of these partitions. So that is based on fork join framework in Java 1.7 or 1.8? 1.7, yeah, 1.7. So reducers are the ones that brought in parallelism, but I haven't seen. I think there were some benchmarks in probably Richie Key's announcement post about how fast the reducers were compared to normal way of using concurrency. So you get to use all the cores properly. So
that's a key thing, is that you definitely get, obviously it's like a lot of these things with fork joins, isn't it? Is if you've got a fairly small data set, then the overhead of the management dominates things, whereas if you've got a very large data set, then
exactly,
you can get into this whole work stealing business as well, and can be very highly optimal.
Yeah. I mean, it's like having multiple people to do the stuff, but if you the division of the work itself is taking too much time, then there is no point in applying parallelism to that one. And so if it takes more time for me to divide a given numbers to be if I want to sum 7 numbers or 8 for the sake of argument, then I have 4 people, and then I need to give them 2 numbers for each, and then they just need to do an addition. Then the addition, the complexity of addition is so small that I'm spending more time dividing the task rather than actually executing the task. So I think it's like there needs to be a lot of, in my opinion, there needs to be a lot of experimentation to see where parallelism is going to help to actually make faster programs. But in a way, that's what functional programming is pushing for, right? I mean, because there are more cores available, but not each core is not going to be as fast as in the past. So
actually, it's quite funny you say that, because I think I told you earlier on that I watched this Guy Steele presentation that Rich Hickey mentioned, and in his documentation, and I think he was asked a question, and I don't know who asked him the question actually, but there's a lot of luminaries in the audience. Someone asked him a question about might have been Joe Armstrong even, I think, but anyway, whoever it was, doesn't matter. They asked him a question about, what do you think about this exact point about modeling for performance in algorithms? And he punted on that, because he said, that's actually the most difficult. That's the most difficult bit. The most difficult bit is actually kind of breaking up the work is fairly mechanical, but determining whether or not it's actually going to be valuable to break up the work is very complicated. And of course, there's an overhead involved in that as well. And I guess if you think about it, it's the kind of thing which probably, and I've just thought about this, but it's, if you think about where we see those kind of things in the real world, is we see them in relational databases, in query optimizers, for example, or in optimization problems in general, don't we? We see them in these kind of linear algebra style modeling things, where you try to work out backtracking solvers, these kind of things. I'm doing a bit of work at the moment on this on configuring product configurations, and it's definitely very, very slippery to work out what is the actual number. It gets back into mathematics of NP hard and NP NP complete, all this kind of stuff. So maybe we should drop that bit of the conversation, because we're going to get completely lost in all of the background stuff. It's interesting stuff, but I think it's like you say, modeling exactly what is the exact profile of things that are going to benefit from this approach is actually unknown.
That's true, but you triggered something like the performance part. So I was thinking, because I've been working, I'm working a lot with Spark and HDFS these days, Hadoop stuff. So it's like sometimes just doing a grep or WC is way faster than actually running a Hadoop program to do the word count, because there is of course, it's not even parallelism, it's even next level up. It's a distributed work. So that means you not only have multiple cores, but you also have multiple machines.
Locality
and then coordinating them and all sorts of crap. But there was something in Clojure World, I think it was David Liebke or somebody who announced this About library that is a distributed state that uses Zookeeper it's essentially like a distributed atom. But I didn't see much action happening afterwards, I think. But that was I think we're talking about concurrency, single machine, single processor, and then we move to parallelism. Of course, single machine, but multiple processors, and then you have the multiple machines, multiple processors. That is a distributed world, and there we don't have any interesting stuff happening in Clojure, as far as I know.
No,
I think the only thing was about
Onyx has that. That's what Onyx
yes,
is
exactly.
all about. Onyx is a hardcore effort at that one. So I think actually they're definitely taking that approach from the ground up. But I think we want to talk about just parallelism and the sort of the programming aspects first. I think we've talked before, haven't we, about we should approach the Onyx guys, and I think they're interested in potentially joining us on one of the episodes.
So maybe we should leave that to when say that Michael or Lucas are going to be on the podcast. That'd be cool to understand the challenges involved there.
The thing, just coming back to this kind of like the reducers thing, the insight I think that Guy Steele made was that functional programming has given us these tree data structures, these tri-data structures, tree data structures.
Tree,
we call them trees now.
I think we pronounce them tree, but it is a TRIE.
TRIE, yeah. So, and in fact, he even mentioned closure in his Fortress presentation. To say that Rich Hickey has got this thing which has these 64-bit data structures. And it's all, it's awesome stuff. I think it's 32-bit actually, isn't it? But
32. 32 level branching factor.
32 level. He said 64, but it doesn't matter anyway. Okay. It all boils down to small numbers.
It's very big.
What does Guy Steele know anyway? But what he was saying was that is that these tree data structures are the foundation of this of the future of how to do reducing and folds and fold out, fold L, all these kind of things, how to do reduce in the future. Because the thing that you cannot do, you should not do in the future, is you shouldn't have these do loops, you shouldn't have these iterations. You shouldn't be forced to iterate over a linked list data structure. So basically, trees give you the opportunity to have a very balanced parallel implementation. And I think Rich Hickey thought, yes, okay. Well, he must have already thought that, but thought, okay. So Guy Steele's definitely given this a good blessing. So let's now make these reducers happen. So what he does there is he basically has some kind of function that does the work, and then some kind of the folding, and then some kind of combining function. So you have these, and the real key thing about it, and the key thing he mentions in it, and I haven't seen his presentation for a while actually, but I remember watching his presentation a couple of times, is that ordering is the death of all parallelism. And that current parallelisms like map and fold, even in closure itself now, and reduce, all start with like 0, or they assume that you're going to have some function, or this function that you're doing, this mapping function that you're doing, this reducing function that you're doing, is aware that you're going to keep some kind of aggregate going through it, so some accumulator, and it's the accumulation that's the problem. So if you can strip out the accumulation into something which the combining function can understand, which is, in other words, it's associative, then you kind of blow away all of the restrictions that you've got in the data structure itself. You don't have to think about it as if it's a vector, or as if it's you can think of everything as unordered, and everything is completely decomposable.
But that is, maybe we should touch upon this stuff more on transducers episode. I was thinking we should dig deeper into this one, and then talk about how transducers work and these abstractions, and probably something for the newer episode. I think we have almost it's almost 1 hour. Wow.
Right. Okay.
I mean, we never looked at the clock, I think, these days. So I remember looking at from the first episode, it's always 50 minutes and then 1.5 hours, and then I think we need to keep it in 1 hour though. But before we move on, I think a quick. So we talked about a lot about concurrency, and also I think we should post the Guy Steele's presentation link somewhere. So we'd post the show notes on defn.audio. But as usual, we'd love to hear your feedback. Whoever is listening, our fans, the plural number of fans who are listening to this podcast, and thanks a lot for listening. And the MP3 will be on SoundCloud, and it is also on iTunes. And next week, I think we will probably try to get a special guest, but we want to keep it as a secret, so we'll announce it as soon as we get some sort of a confirmation, I suppose.
Yeah.
And of course, thanks to our very talented Pizzeri, I think. Am I pronouncing correctly?
Yes, Pizzeri, yeah.
Pizzeri for giving us permission to use the track. And what is that called? Melon hamburger?
Yeah, it's a vegetarian hamburger.
Okay, yeah. Oh, okay. So obviously the music is also vegetarian. So this is the number one vegetarian closure podcast on this side of the pond, with an Indian and a UK Brexit guy.
I am not for Brexit. But anyway, bye-bye.
Bye-bye.
Cheers, guys.
Okay, thanks for listening, and we'll push the new episode in a couple of weeks. Bye-bye.
Bye.